that's kind of our vision of getting to a 300-mile range vehicle, but still have the 15-minute fast charge capability. I do think this process is compatible with dry battery electrode technology or manufacturing approaches. We can make design decisions that enhance multi-layer overall using that particular dry manufacturing technology. We can drop into an existing line in any factory and begin manufacturing multi-layer electrodes at the same speed and scale that is required for kind of gigawatt hour or terawatt hour production.
Earlier today, I had a great conversation with one of the co-founders of EnPower, Adrian Yao, and I was able to talk about their multi-layer battery technology a little bit more in depth than I did in the past video. Several of the questions that I was able to ask Adrian were inspired by some of the comments that those of you who watched that first video left. And so I hope you find Adrian's answers helpful. I know I did. And it's a great conversation. I'm really excited to share it with you. For those of you who have not watched the first video that I published about EnPower, I will link to that in the video description. But without further ado, here's my conversation with Adrian. Welcome, Adrian. I'm so thankful to have you come on today and to talk about the EnPower's multi-layer anode, really electrode technology. So thank you so much for taking time to talk with us today, Adrian.
Thank you. Thanks for also making the previous video, John.
Definitely. I know you had mentioned that you had something to respond to for that previous video that we did. We'll dive into the questions that I prepared after that, but go ahead and address what you had mentioned earlier and just talk about what you want to there.
Yeah, I really appreciate you kind of scoping us out and talking more about us and kind of bringing us to the forefront. The thing I wanted to first address is that I really appreciate the mention, but I do want to address the title. I fundamentally am kind of averse to using language like the battery that does it all, because I think I'll be the first to say that there is no battery that does it all. I think that is a misconception that the battery industry needs to get over, is that there is no such thing, unfortunately, as a holy grail. And I really think that word needs to be eliminated from all future talks about batteries, because it's so easy to, well, batteries are just so hard of a topic that, and it's so easy to use hyperbole and get over. So while our technology that I'm happy to answer more about will address this fundamental energy power trade-off and really expand the operational range of batteries and really address this quote unquote and problem that we can talk about more later, I don't want to give the impression that it does everything, because there's, apart from just energy and power, there's so many other things that need to be addressed that I think lithium-ion has a really good chance of solving. But I just wanted to first throw that out there, is I appreciate the video, but I do want to make sure that ultimately what sells is a quality product and not the language. So, but
I do appreciate that. Yeah, I think that you're right. I will go back and I will adjust that, because I don't want to overhype something. And, you know, you're right. There really is no one battery technology that does everything. And so that's a good balanced view. And I appreciate that honesty, and definitely appreciate the feedback on that.
I obviously want it to be the best battery out there, but ultimately the product will sell itself.
Totally. I can respect that, and I appreciate that. So let's dive into the multi-layer anode and really electrode technology. And what I want to start with first is kind of the origin story of the technology itself. Did this technology exist elsewhere and you just brought it in and you're implementing it yourself? Or is this something you guys came up with as a team? If you could just kind of talk us through that.
Yeah, I founded the company way back in 2014, coming out of Rice with two other PhDs at the time. And what we were really focusing on then was actually figuring out how to manufacture differently, manufacture batteries in a different way. And we were working off of this process using a spray deposition process. And that's fundamentally different from how batteries are typically made today. And with this spray deposition process, we could conceivably additively manufacture a battery. So you can think of it more like 3D printing. You can 3D print the cathode first, and then the separator, and then the anode, and so forth. But that's really ahead of its time and not really practical when we realized. But taking that and leveraging that same kind of approach, we realized that there was a really big opportunity in engineering and additively manufacturing just one electrode, right? The electrode itself of inside any given battery is going to see a difference in properties from the current collector, the metal foil, all the way to the separator. And that's just how batteries operate. They're gradient forming devices naturally. And so it only makes sense from a first principles perspective to engineer an electrode that responds and counteracts those gradients, because they can be detrimental. So additively manufacturing an electrode, kind of spraying layer by layer, was really the approach that we took for a couple of years. And initially we were able to prove the principle that works. The problem really comes down to this can't scale, right? There in 2017, we kind of hit a wall, understanding that there's no real way that you can convince someone like a Panasonic, a CATL, LG Chem, you name it, to throw out their $10 million plus line, the coating line, and swap it into something brand new that's not yet proven. So that's when we really took a pivot and figured out how can we make these multi-layer architectures, again, addressing the same fundamental problems inside batteries, but do it in a way that's scalable, and do it in a way that's a lot more drop-in to existing infrastructure. And so that's where we stumbled upon some of the coating techniques used in the photographic film industry and other industries like adhesives, where the multiple layers are simultaneously deposited. Now, not everything is translatable, but from those industries, but that's really where we focused our efforts on, and can now proudly say that we can drop into an existing line in any factory and begin manufacturing multi-layer electrodes at the same speed and scale that is required for kind of gigawatt hour or terawatt hour production. And so our ability to recently, last year, we acquired the former Anode facility in Indianapolis. And that really is what allows us to kind of walk in, drop in our new coating head, and kind of be off to the races.
Yeah, that's really important. I like that you took, the initial idea and you've now developed it further into something that's scalable. A lot of times when you hear about these exciting new technologies and it's coming out of, universities and things like that, and that's important, that's exciting, but it's not often scalable at any level. So it's great to hear that it's going to the next level, more of a scalable approach now with what EnPower is doing.
Yeah, and that's been we've been using that process ever since 2018. So it's been the majority of what we've been doing so far.
Very good. Now, something that was brought up, it's brought up in your website. You talk about, and I want to talk about the simultaneous coding, how that works in a second. But one thing was brought up, a YouTube commenter brought this up in the comments section. I can't remember if I mentioned this in the video, but on your website, you talk about with these multiple coatings, it can be the same chemical makeup of a standard homogeneous single layer electrode, and it also doesn't increase the thickness. That seemed to be something that, at least one person was questioning how that's possible. So I want to bring that topic up. How can you have a multi-layer anode or electrode in general and not increase the thickness? Like, how does that work? What does that look like? And within that, if you could talk about the simultaneous process, how does that get laid down at the same time?
Yeah, so I think there might be a little misunderstanding there. So basically, if you think of an electrode, and electrodes in batteries are not very different from a spongy cake. It actually looks quite like a cake because it's a porous composite. So what we're doing is taking, say, a cheesecake, right? We're taking a cheesecake and we're just slicing it across and splitting that into two layers. And of course, we can begin changing what we do in those two layers, right? We can use more, I'm clearly not a cake baker, but you can choose a different recipe on the bottom. You can add, add more sugar or use a different cheese. I don't know if that's done, but that's how we would create with two different layers. So it's not so much that, so it's basically that we're changing the formulations in each given layer. We're choosing those layers respective to, or to really to optimize the performance inside of a cohesive electrode. And that's how we get to our designs. It's not so much of taking a homogeneous, electrode and then somehow making it multi-layer. I think ultimately that's not how you would design a cell in the first place, right? You would design a cell that works best. The reason for these homogeneous baselines that you've referred to and we talk about in the white papers that we've published is that is the best way to do a baseline apples to apples comparison of how the technology works. So take our multi-layer cheesecake, for example, right? Say we have cheese 1, cheese 2, sugar level 1, sugar level 2, and a cake. What we then do to baseline it and to ensure that, hey, what we're doing is actually useful is that we take those 2 layers, blend them together at the exact mass ratios, and then make a cake as you would traditionally a cheesecake with the same thickness and the same porosity and so forth, and then test side by side. And the benefit that we then see will be directly a result of the performance benefit of the multi-layer architecture. So again, it's not so much that we're taking existing designs and kind of somehow doing some magic on them and making them multi-layer, but somehow not reconciling with the thickness problem. I can see where the YouTube commenter comes from, but it's really not that. It's really, we're starting with a multi-layer design and ensuring that is actually useful. The multi-layer, the homogeneous baselines that we end up making will not go into the market. They will not be products because they will be inferior.
Can you talk through that process of simultaneously coating the electrodes, that slurry process? What is that? I mean, I know you're probably not going to dive into things that are protected maybe by IP and secrets and stuff, but how does that head, you mentioned the head there, the coating head, what does that look like? What is that doing? How's that doing this multi-layer process? Like, talk me through that.
So traditional battery electrodes are manufactured using what's called a slot die coater. So a slot die sounds kind of like what it is, but I like food analogies because everyone can relate. A slot die head is a glorified mayonnaise dispenser. You know the mayonnaise dispensers that have a slit and then you kind of squeeze it and so it's already kind of like flat on your bread? That's a slot die. A slot die is the same thing. So the difference with our dies is that we have two slits, and the 2 slits are sourcing 2 different slurries, and the 2 slurries are obviously mixed in 2 different pots with different formulations, cheese 1, cheese 2, whatever you name it. So ultimately, they meet right at the head when they're being dispensed onto a moving web of foil that then goes into the oven to be dried. So it's not unlike Crest toothpaste, right? The one where you get red, white, and blue all in one stream, and it maintains its actual colors, or the colors don't mix, otherwise they wouldn't do that. And so it's a similar concept is that as long as you maintain sufficiently high viscosities, and obviously there's some engineering there and ensuring how the layer interfaces interact with each other, that's how we can maintain the structures coming through in a wet process.
That makes a lot of sense. Definitely. I appreciate that clarification. Now I just kind of want to move into, I addressed this a little bit at a surface level in the video, but we talked about how your technology allows you to create a power dense and energy dense cell. How you can have the 2, and that's not ordinary in a lithium-ion battery, to have both optimized. Could you talk a little bit about the technical side of that? What is it about these multi-layer anodes that allow you to achieve that good balance of energy dense and power dense battery cells?
Yeah, so like I mentioned earlier, batteries are inherently gradient forming devices, meaning when you during operation, concentration gradients will form, and that's not something that that's kind of a fact of life. It's not something that you really want, and so typically to get really high power, you end up making thinner electrodes because the physical distance that lithium ions need to travel will be less, and typically power electrodes are also more porous, so that there's more room in between active material particles like graphite to make room for the lithium ions to move. Of course, when you have thin electrodes, you then have a lot more layers of copper, aluminum, and separator that aren't contributing energy. And because they can also cost more, the power cells are not only less energy dense, they're also generally more costly. On the other hand, you can make really high energy density electrodes by making those electrodes really thick, also compacting them to really high densities. But naturally, lithium ions then need to travel longer distances. And they also have a much more tortuous pathway. That's a technical term, the tortuous pathway to make it through and squeeze through the pores of all those active material particles. And so naturally, their rate of movement suffers and your power will fall. Ultimately, your current capability is kind of a balance of what your electrons can do and what your ions can do. In a lithium ion system, and probably most batteries, the ion movement is limiting. And so that's really where we want to be engineering towards. With a multilayer electrode, we can engineer a thick electrode so that we can maximize energy densities. But what we can critically do that typically cannot be done is we can engineer the structure in a way that promotes a more rapid transport of those lithium ions, right? We can make the top more porous. That's kind of the easiest way to understand it. And you can think of it as cake too. You can make the top layer of your cake more porous so that there's a lot quicker lithium ion transport. And so you, in a way, counteract that concentration gradient. And then as they get deeper in, you can increase the densities. So that's one way in which we can tailor the performance. The porosity is the easiest. The porosity example is the easiest, but is not by any means the only lever that we have to pull, right? So the particle size of graphite or cathode, on the cathode side would be a different material, but the particle size of the active material also makes a difference. There's, apart from porosity, there's also a more technical thing called tortuosity, which is, I'd argue, to be more important. And that's kind of going back to what we talked about earlier. It's related to porosity, but not always the same. But there's also other things like the actual material itself. In a completely graphite-based system, of course, both active materials will be graphite. But as you know, and as many people on your channel know, and I think most people or many people in the know of batteries know that there's increasing levels of silicon doping into today's cells, right? Silicon is a different material from graphite, which is carbon-based, but silicon has much higher capacity, specific capacity, but it has some critical problems with it, including cycle life and calendar life, that limit its widespread use. But because of its capabilities, people dope it in and sprinkle it into your electrodes. Now, that is yet another kind of design variable that we can use to our advantage, and specifically put that material where it matters most in the electrode. And maybe I won't talk about exactly which layer we think it should go into, but fundamentally, from a first principles perspective, understanding that lithium ions only have one way to go in and one way to come out, there is a right strategy to make a multi-layer electrode be optimized. There's also a wrong strategy, and we can definitely make electrodes that perform worse, but that's obviously not what we try to do.
That makes a lot more sense now, how you can have both, because really, how I understand it now, you're eliminating a bottleneck, which is the main reason why they make a power cell like they do. And if you eliminate the first principle reason that you have to make those electrodes thinner, and you just fix that problem, then you can have the thick electrodes and have a power dense cell. So that makes complete sense now. It was kind of confusing before, but your explanation is helpful. I think that'll be helpful for those listening. I understand it a lot more. Now, with that same principle, that I think will tie right into charging speeds. From how I understand that, a lot of the things that you talked about there also relate to high charging speeds. When we talk about a high power dense cell, that's related to charging and discharge rates. So talk about how that relates to fast charging, and then we'll move into life cycle after that. But how does that relate, and kind of relate that to fast charging performance of this battery technology?
Yeah, well, really, fast charging and life are intimately connected. They go hand in hand. So I think answering one will answer the other, but we can certainly expand on the other, the latter one later. But in a lithium-ion battery, when you're charging, that means that you're taking lithium ions out of the cathode and then you're sticking them into the anode. So in this case, the anode in our conversation is graphite based. And the key risk in lithium-ion batteries is that the reason why we call it lithium-ion batteries is that lithium metal batteries actually predated lithium-ion. The first batteries that were of this class were commercialized in 1989 by Moly, and they used a lithium metal anode. And of course, one of the problems with lithium metal is that you have dendrites form, and they also use a liquid-based electrolyte. So that eventually caused problems when they began short circuiting and resulting in some battery fires. So they had a recall, and that's really where Sony came out with this new design, where instead of using lithium metal as an anode, we're going to swap it with a carbon host. And that time, the carbon host was petroleum coke, but graphite really functions the same way in that it doesn't make lithium go into its metallic state. It still hosts lithium in its ion state, hence the name. And so that's critical. And so lithium-ion batteries always have lithium ions in their ionic state, at least when charged correctly. The danger comes when you try to charge too fast, or when you're trying to charge in too low of temperatures, or both. And in those situations, what you end up doing is that you cause lithium ions to convert into their metallic state. And that metallic state will deposit on the surface of your graphite electrode. That is obviously bad because apart from the growth issues that we talked about in its ability to eventually create safety concerns as it punctures the separator and causes short circuits. But lithium metal is in general just something that you want to stay away from because it immediately reacts with the electrolyte. It causes irreversible capacity loss. It increases the impedance of the cell, so your cell will heat up more through operation and therefore kind of exacerbate aging concerns and so on. So really, so fast charging lithium. This entire phenomenon is called lithium plating, and it's the concern that we always want to mitigate. Now, lithium plating is intimately tied with those concentration gradients. You can imagine if you have a really thick electrode, and that's really dense, and lithium ions have a very difficult time making it through rapidly, but you still pump it with a bunch of current. Then what's going to happen is that you're going to have an overconcentration at the surface where you have that bottleneck that you talked about, and that will cause lithium metal to deposit. So if we can enable the surface of the electrode to be more, for example, porous, as using that same example, and to enable a more rapid transport of lithium ions to access not just the surface of the materials, but all of the materials in the electrode, then we can balance the state of charge throughout the thickness more evenly and prevent lithium plating from happening. So that's fundamentally how multi-layer technology works. Of course, if you blasted it with some current that it wasn't designed for, you're still going to end up with the same result. But the key difference here is that since these electrodes are now intelligently designed, from a first principles point of view, right, then you can increase your operating boundaries in the power regime while still maintaining a certain energy density. So that's kind of our vision of getting to a 300-mile range vehicle, but still have the 15-minute fast charge capability.
Perfect. Okay. Appreciate that. I'd like to now move over to the fact that, from everything I read on your website, you're focused on these multi-layer anodes, multi-layer anode technology. It was either an article, I believe it was an article on the website, you mentioned that you can also apply the same technology to the cathode side. If you just could explain maybe why you started with the anode first, why focus on the anode and not the cathode first? And then if we could talk about, what benefits could be achieved if you did the same technology to the cathode.
We focused on anodes first because fast charging was really the key, right? The cathodes don't have this fast charging problem because electrochemically speaking, they don't suffer from this risk of lithium ions converting into their metallic state. That's really an anode phenomenon. And given that the kind of electric mobility, it depends on fast charging, especially for example, the 40% of Americans that don't have a vehicle, don't have a garage to charge their vehicles. Supercharging or fast charging of vehicles will become a bottleneck to electric vehicle adoption. So, seeing this in 2018 is really when we really kind of drilled in on the anode specifically. We actually did our initial spray deposition processes on the cathodes because it can still be done. But yeah, it's really driven by what does the market need, and how can we provide that value. So that's why anodes first. We're now also using the multi-layer technology, coating technology on the cathodes. It's really no different. You're just mixing in two different pots and you're depositing it in a similar way. Of course, the solvents are different between anodes and cathodes in commercial manufacturing, but as long as we control the rheology or viscosity of the electrode, the slurries coming out, we can still maintain that multi-layer architecture. The levers that are available to us to pull is arguably less on the cathode because it's the cathode side. It may be a little bit more chemistry specific, but there are specific kind of levers that we have identified that we can engineer, and what we would engineer towards is still towards improving the lithium-ion transport through the entire thick electrode, and also cycle life. So those are the two kind of areas that we'd expect to see additional boosts in performance, specifically discharge power, not charging. You're not going to get faster charging really by working too much on the cathode. Eventually it will become a concern, but I think it's for the most part, the cathode will dictate discharge performance and also cycle life. So those are the benefits that we expect to see.
That makes sense. So the anode is the weak spot that really needs the most improvement and to see the most important gains in charging speed, et cetera. And then you can move to the cathode later on to kind of get those gains, the further gains later on. Okay, that makes a lot of sense. Now, from this conversation and just kind of talking to you about this process, this multi-layer process, it seems to me that it doesn't really add a lot of complexity to manufacturing. But could you just address that a little bit? The scalability of this multi-layer technology, how it compares as far as like production time. If you take two production lines, one is using a standard process like most companies are using, and the second line is using this multi-layer process. Is there any slower manufacturing with this multi-layer process? Is it more complex? Does it require a bigger machine? Like, what's the difference? What does that look like? How scalable is it?
Yeah, so driven by your first question about, or coming back to the first question you talked about with respect to, how did we come across this approach? We started off with something that's completely unscalable, and then figured out how to make it scalable. And the beauty really does come down to the keep it simple, stupid kind of a mentality here. So in that sense, it is very drop-in. In terms of system complexity, there's obviously going to be just the fact that you have two different slurries as opposed to one. There's obviously going to be that increased level of complexity, but overall, I would say that there's really not much. Instead of mixing one slurry, you're mixing two separately. They don't meet until the point at which you coat, and so you're obviously going to need multiple pumping systems. But based on the coating speeds that you can achieve and the coating yield rates that you can achieve are not going to be detrimented. And the cost of the materials that go into the electrodes, so long as you're using commercial off-the-shelf materials like graphite that is commercially available, that will not be affected. So ultimately, when modeling this in kind of a techno-economic model, we do see very little impact. We use this model called BATPAC. So it stands for the Battery Performance and Cost Model, and it was developed by Argonne National Lab. It's on like version 4 or 5 now. But basically, it's a really kind of robust model that models everything from your material inputs all the way to an electric vehicle pack. And so the assumptions that we took in the modeling is that, okay, if you were to kind of do what you talked about, if you were to make side by side conventional electrodes versus a multi-layer electrode based cell, in this system, the things that you would need are, you'd obviously need more mixers and more manufacturing footprint, and to be conservative, right? You just basically double everything, double your mixers. And then obviously have just the cost of the coating head, which is not much compared to the cost of a coater. So it's a minor expense. When these plants are running at gigawatt hour scale, the same coater is servicing millions, if not billions of batteries, depending on the size that you're making. And so ultimately it gets depreciated significantly, and kind of normalized. So ultimately we end up with a less than 1% dollar per kilowatt hour base difference. And that's well within manufacturing noise. So ultimately, the cost of a cell is dominated by far by the materials that you use. And that's why there's so much pressure on, for example, going from NMC to LFP type chemistries because of the cost. And so as long as the materials in which you're acquiring are the same, there's really going to be very little difference in the ultimate manufacturing cost.
That brings up a question. I'll move back to manufacturing and your pilot production progress, et cetera, in just a second. But this is actually something someone else brought up in the comments. And then actually, it's something I'm curious about as well. Right now, obviously, you've described a wet process, the slurries and the multi-layer and that approach and mixing that. But obviously, the dry battery electrode, that's something that a lot of people are talking about, that dry process of manufacturing electrodes without the wet solvents. And, obviously, that reduces the amount of factory space you need. You do have somebody on your team who has experience in that. I know there's probably IP that's protected by patents and things like that. So you may not be able to just plug and play technology from the Maxwell Technologies, Tesla dry battery electrode technology. That being said, is that even possible with this multi-layer approach? Technically speaking, just fundamental, not is EnPower doing it, but fundamentally, do you think it'll work with this process in the future? And then I guess you could also say, is that something that EnPower is even thinking about in the future, like about possible in the future? If you could talk about that a little bit.
So number one, multi-layer technology is the most important part of multi-layer technology is what you make, not how you make it, right? And so the architectures itself are really what we care about most. If you can manufacture it cheaper, all the better. So that's number one. Number two, I do think this process is compatible with dry battery electrode technology or manufacturing approaches. And of course, and actually I would say prior to this particular individual that you're talking about joining the team, we already have had some movements in the IP space. So our ability to do it is not really dependent upon some of these issues. I'm just being a little careful with my words here around kind of what is out there. But ultimately, I think this is something that we are interested in. And I don't see a path in which I don't see something that would get in its way. I think ultimately we could even make we can make design decisions that enhance multi-layer overall using that particular dry manufacturing technology. So yeah, I think it is compatible, and ultimately what matters is what you make.
It's good to hear, because I think in the future that's going to start dominating manufacturing. It may take a decade before it really rolls in because there's a lot of old processes people are using, but it seems like it's the future of the lithium-ion battery manufacturing. So it's good to know fundamentally it appears like it'll work. I'd like to move back and then kind of, as we start closing the conversation, talk about how do you move from prototype to production. I'd like to first of all talk about, in your opinion, share what you can. What do you think some of the limiting factors are right now that you're trying to work to solve in order to get from a prototype bench test cell into a production battery cell? And then I want to talk about your progress with your pilot production facility and what you're building out there in Indiana.
Yeah. So great question. The biggest impediment to getting product on the road from where we are with initial prototype cells is an entire piece called product development. And this is something that I think, when you hear about new battery technologies, you don't immediately think of that because, of course, including this conversation, what's important and what is of interest is how does technology work? What are the scientific and engineering principles underlying its ability to function, and how do you end up with something better? But ultimately, that doesn't matter. Right? Ultimately, what matters is that you can put a product in the right package and the dimension that someone will be willing to put into their vehicle that floats, rolls, or flies. Right? So that entire piece is product development, and that's where you have to make the critical trade-offs between cost and the same energy density, power density kind of trade-offs that you have to make, albeit with multi-layer, you get a expanded operating window, so you have that to your benefit, and that's really where you design something to a customer's needs. That is where we currently stand. That's where we're developing and coming up with a product and a portfolio of products to manufacture. That is our biggest impediment. It's not really an impediment, it's just a necessary step, and a lot of the hard work that needs to happen to get to a point where you're selling product. Because of course, and maybe this isn't obvious, but if you develop a technology, it doesn't mean it sells, right? You need to convert it into a saleable product, and that is non-trivial by any means. And it's the tough work we're doing right now. I'd say along that, given the fact that we made a build or buy decision in terms of when we transitioned from a licensing business model to a product company model, we made a build or buy decision or analysis of, what does it take to go build a factory, and what actually exists out here in the United States, because remaining local and remaining domestic is important to us. And so that's where we kind of came across the former Anode facility that we now have acquired. And the differences are significant changes in lead time, right? Just given how hot battery manufacturing is right now, just to get equipment like the slot die coaters, or not even mentioning dry at the moment, but just getting coaters and equipment, it's like a 24-month time just to get things out the door. So this is a really quick, acquiring an existing kind of brownfield plant is a really quick way to get to the market. It comes with its challenges, of course, especially with, bringing equipment back up to operational state, but that's just the necessary work that you have to do when you're manufacturing.
What can you share about your progress at that facility, building that out? Because I think you're getting somewhat close to making some announcement of that opening up. I know you guys shared some photos with me about some things going on at that facility. What kind of progress can you share publicly? Maybe you can't share much yet because you haven't made the official announcement, but anything you can share about that progress there?
Yeah.
And are you still reaching for, I think it said in 2023, 800 megawatt hours of production per year, I think, expanding to?
That's the goal by the end of 2023. But yeah, we stepped foot into this facility in the first week of January. And so in the last 9 months has just been, 8 months has kind of brutal work of bringing equipment up and actually getting first cells built. So we are building cells, and we're testing prototype cells. We anticipate having first cells for commercial qualification by the end of this year.
Well, I think that's a good overview of this technology. You've answered a lot of good questions to a level of technicality that I think a lot of people can understand, even if they're not experts in battery technology. So I appreciate all that. I like the approach you guys are taking. I like the non-exaggerated approach you have towards this technology, and the realistic approach that's always refreshing in the battery industry, where it's often overhyped.
Yeah.
And appreciate that for sure. And Adrian, thank you so much for taking time to come talk to me about this important topic.
Of course. Thanks so much for having me.
Do let me know what you think about all this in the comments section below. And also, if you currently work in the battery industry and you'd be willing to share any insights or clarifications with me, feel free to email me. My email address is john@cleanerwatt.com. Well, thank you so much for watching this video all the way through to the end. I would like to once again thank the Patreon supporters who support me every month and help make this content possible. A special thank you to my performance supporters and also the other supporters listed on the screen. If you'd like to find out more about the Patreon community I've set up, I'll put a link in the video description. Thank you so much.